Conditions within gas turbines are often intense, with extremely high temperatures and pressures. To prevent damage to the rotors and stators, air is used as a coolant. In this model, thermal stresses are analyzed in a stator blade with internal cooling. For this structural mechanics heat transfer example, we want to add thermal stress as our physics choice and use a stationary study. The parameters have already been created and represent gas pressures, velocities, temperatures, and other relevant properties for the cooling channel. By adding an import function, you can browse to the model's Model Library folder and select the turbine stator geometry. Click Import to bring it into the graphics window and use the transparency button to see the interior of the stator blade. To simplify the model setup, explicit selections have been made. The first explicit defines the internal cooling duct boundaries. The second explicit defines the boundaries in which heat is exchanged with the rest of the turbine. Open the material browser and go into the material library. The entire turbine stator blade is made up of an iron alloy, which we will add to the model. As you can see, Poisson's ratio value field is empty, so we will enter 0.33. To start the physics setup, we want to show the discretization tabs. Under the thermal stress node, we want an equal order element type and U1 plus T1 thermal stress fields. In the thermal linear elastic material node, the strain reference temperature is increased to 300 Kelvin. In the initial values node, we want to enter in T-gas for the temperature, 1100 Kelvin, to simulate the high temperature combustion gases. Now we will define 5 boundary conditions for defining heat exchange. Under the heat transfer node, add a heat flux and select the exchange boundaries explicit created earlier. We want an inward heat flux with a heat transfer coefficient of 25 and an external temperature of 900 Kelvin, the variable T-work. Define another heat flux in the cooling duct using an Nusselt number correlation from previous studies as the heat transfer coefficient. We want the external temperature of the cooling duct to be Tcool 800 Kelvin. A convective heat flux boundary condition is added to model convective heating in the stator blade boundaries. Using an external force convection model, the heat transfer coefficient is automatically computed as a local transfer coefficient. Input values are needed for the surface position along the plate and fluid flow properties: velocity, pressure, and temperature. For the second convective heat flux, we can duplicate the first one. We need only to edit 2 factors: the boundaries on the suction side of the stator blade and the velocity. Duplicate the second convective heat flux. The third convective heat flux includes the sidewalls perpendicular to the stator blade. We want the same temperature and pressure as the other 2, but different position along the plate and velocity. Adding a roller boundary condition simulates force of the track on the stator blade when in motion. 2 spring foundations are created now. The first applies force in the x direction with a spring constant of 1 E9. The second spring foundation is in the z direction with a spring constant of 1 E10. To finish off the physics setup, a prescribed displacement has been added for point 16. A prescribed displacement constrains the turbine stator blade to a unidirectional movement in the y direction. In the Mesh node, clicking Build All starts the mesh sequence. Now we can right-click the Study node to compute the model. Two default plots are created, a stress plot and a temperature plot. A great feature in Kامسول is the ability to view the magnitude and location of the maximum and minimum values on a surface plot. Click Replace Expression and choose Thermal Stress Solid Mechanics, Stress, von Mises Stress, and click Plot. The second default plot shows the temperature distribution. Clearing the Plot Data Set Edges box and clicking Plot removes the original geometry. Create a 3D plot group and a volume plot to view the displacement. Go to Replace Expression and choose Thermal Stress Solid Mechanics, Displacement, Total Displacement. Select millimeters from the unit list and click Plot to see the total displacement throughout the geometry. Learn more about this and similar models at kامسول.com/turbine-stator-blade.